Thank you, everyone. So today I'm just going to go some overview of our seismic and data analytics efforts that we did for Metal Earth Geophysical Data. Again, lucky for me that Richard and Dave were laid down some of those basics, so it's going to be very easy to me to describe these. Okay, put this one. There we go. Okay, so just the basic thing. So Metal Earth, we know about the purposes of that. So for seismic, we've done 1,000 kilometers of active reflection seismic. On one of our transects, we did a passive seismic, and these provided us with reflectivity, PS convertibility, and velocity information that we could really combine, at least in one of our transects, and get some data. So we did 3D density, resistivity, and susceptibility inversions from all the data that were available from the Geological Survey of Canada. And then we did all these cluster analysis, then I'll go to basics, how we manage those, and our researchers would use those data for their data analytics. Again, going to just the overview of where our transects are from the east, from Shibugumi starting, covering all these Abitibi area, and then we have all the zones of the Wabigoon transects. The black lines you see there is our Metal Earth transects. You see blue lines, those are the lithoprobe data that they were acquired in 90s and 80s and 90s. And there's a little zone in here that we have the Discover Abitibi data, that purple line. So there's lots of seismic, and we try to fill in our seismic within those transects. Again, just focus on what the Abitibi and the Wabigoon zones are, and how we were trying to compare a fertile zone to something that looks like less fertile on the Wabigoon. So going to seismic, what the seismic insights we got. So I'm just going to focus on Larder Lake. Glad that Richard talked about that. So on this transect, we had 44 kilometers of the active seismic, which is the reflection seismic. And that's done in 2017. And 2019, we did a passive seismic. So we lay down these broadband 4D seismometers. They recorded for 40 days continuous. And we were able to generate two kind of independent information out of these passive seismics. One, shear wave velocities that we estimated from surface waves, ambient noise. And we also used during that time, there were like 20 or 30 big earthquakes that happened all over the world, and they were able to record it, and they got some receiver functions data. So they were independent data, and we could really combine them with our seismic interpretations. So this is what the typical after pre-stack time migration that's our seismic section for Larder Lake looks like. Again, so what we did, we tried to enhance these dips. We call them dip, like using curvelet transform or dip coherency. You can do that, and you can see, you notice these kind of reflections, and you see these dim zones, which is like, this is pretty much matches with the Larder Lake fault. And again, one of the basic, what's most useful we find from this, it's coming from Olympic down from Australia and all that. If you lay down the conductivity, resistivities, you see these red ones are conductive zones, they're pretty much matching with these shear zones and the fault zones. Anywhere you see like a dim seismic zone, the aseismic we call it, we see these kind of like conductive zones coming up. So which is very, again, I'm showing here for Larder Lake, but all of these are published for all of our transects by Simmons, and they're online. You can just go and look at all our transects with seismics and resistivity combined. So we take these and just gotta look at them like with the lithology on top. So if you make a 3D model, it's really interesting to see how these things evolve, and you can see like how the faults and things are combined. So I'm just gonna go here. So this is our Larder Lake, and about 15 kilometers to the west of this line, we have another lithoprobe. So it's very interesting when you just rely on one transect, something like that, things become hard to interpret. But if you have another seismic section nearby from any other data set, when you put these side by side, you can do way more stuff. So like get interpretations like really restrict and get a better interpretation of data. So for this purpose, that's what we did. This was the transect from the litho probe. And we were seeing, if you focus in here, I don't know, you see it in there, you see these like parallel dipping down reflectors that they somehow on the surface, they end up to these are magnetic anomalies you see there. They're parallel there and they're just going down. And these are our mafic units from the lower Blake River. And it was interesting to see that this are like ending in here. So this is obviously, this is the same lithology going all the way down here. So we were able to pretty much nail down where our upper cross limits are, and these mafic rocks, mafic volcanic rocks terminated there at that level. And you see again, these are all interpretation at this point. We say there's a dim zone, most likely something is coming from up in here. And then you combine all these, and you can transfer that to your section in here, and you can just get some sense of what your reflections are. I talked about the passive seismic. I'm not going to go through the theory of that. So we have it on the background in here. You see our active seismic with the reflections. And our passive seismic with the ambient noise tomography, we were able to get shear wave velocities. So in oil and gas, you usually, once you have a seismic, you drill down, you well tie, you always see just the logs, you see where the density is and velocity. We don't have that glory in here. But having this independent passive seismic section, doing the simple 1D inversions, you get high velocities and low velocities like where they are. You can see here, we have this reflection in here. On the top we have high velocity, and the bottom we have low velocity. And that really gives us some really confidence that this reflection is caused by high velocity on the top and low velocity on the bottom. Again, these inversions come with some kind of uncertainty analysis. You can really say, okay, I wasn't on, they do stochastic inversions. And you can dim out. So anything you see I dimmed out in here, we were not certain. But anything it's not dimmed and it still has color, we were really certain. Those inversions really had a really good certainty. So we were able to say, oh, this is our mafic volcanic unit, high velocity, and there's a felsic intrusive things that coming right under there. So you can really nail down. This high velocity in here must be a mafic intrusions of some sort. So these kind of independent information really helps to reduce your uncertainties and your interpretations. And I talked about that the receiver functions with using the earthquakes that happened during that passive seismic. It gave us this really interesting dipping, I don't want to get subduction because we call it the delamination, that feature that kind of has a higher velocity, there looks like something happening here. And right at this zone we see this intrusion, something coming out from here. So that's another thing we use from, if you have many data, you can use them to do some interpretation. Again, this is published in our paper in 2022 if you want interested to look at it. So just generally, if I put 3 of our sections in Abitibi, these are our seismic sections on top, and I put 3 on Wabigoon. Again, the goal was, what is the difference between Wabigoon and Abitibi? It's really hard to say. I think these are pretty much the same kind of geology, the same kind. It's very difficult to say what the differences are. The Shibugumu might not be a representative of all the other Abitibi zones. So it's in the seismic, it depends on the location and how you interpret it. What other thing I did, I just estimated interval velocities from our stacking velocities we do in reflection. What I noticed the most from in here, I see in Wabigoon we have this green and yellow, red zones. These are the high velocities, more continuous in the lower crust. And while in our Abitibi ones, except the Shibugumu, they are more the kind of the disrupted, and they're narrower zones. And that's kind of thing I feel that's could be made one of these, but again, each of these intersect, transections, it's better to be interpreted independently. So having had that, I'm just gonna go what we did with the other data sets, that's seismic done, going to the potential fields. We have the gravity data from GSC. That's, again, these are an average 2 by 2 kilometer sampling rate, I would say, and then we take them to inversions, and it's really fairly covered on the surface, and inversions gives you a really decent results of the density values. And then here's the location of the Matheson the Matheson area that I'm just extracting from this whole inversion. In the same zone, if I go to the Matheson, this is our magnetotelluric resistivity inversions. So again, most of these things people, we already talked, Adamola and Eric, they worked on these. You notice that that's one of the things like with the resistivity. Our magnetotelluric stations were like along the profiles, transects, we just put them like few in there, and they're pretty much along the lines. And we're doing a 3D inversion of this. The ideal case for resistivity, this would be like we really had the regularly spaced stations here. We have few empty stations from lithoprobe that they're around that we can use to confine. But this brings that when you're working at the resistivity data, they're mostly valid along those lines, even though we're making a 3D volume. So we have to really keep that one in our minds too. And here is our susceptibility. Again, this is in a 200 by 250 by 250 meter resolution. These are in the GSC, free there, you can download, and then you can invert them to susceptibility maps. So once we have all these 3 volumes, they will come in all different sizes and extensions, and you can see their overlaps in here, the density model. And so what we did, we just go to the area that all of these are combined, like they're overlapping each other, because for our analysis, we wanted all 3 of these physical properties to be available at every location. So that's what we did. We take the density, they were more coarser, we interpolated, make it smaller. I choose 500 by 500 meter horizontal, and also in the depths on a 500 meter sampling. So to make a regular grid. So here resistivity, and some zones were like, again, irregular, we just make them. Everything's resampled to 500 by 500 by 500 meter cube. And now you have at every locations overlapping values of the density, resistivity, and susceptibility. So once you have something like that, you know every point, you just take those points and throw them in this graph. It's like it looks like bees worming around. So you have resistivity, susceptibility, and density, and you can start doing interesting things, clustering analysis, and see how they look like and where they end up with this. So just before doing that, so let's say we have a lithology too. We have now 3 cubes. On the surface, I want to know, sample my lithology too. I want to see at every 500 meter what are my lithologies are, and that's what I generated on top. And again, at every depth, so every 500 meter I'm going down, I'm just showing samples depths up in here. So at 14 or 15 depth levels, I have all these slices of density and resistivity and susceptibility. Again, looking in here, I'm just at different depth, I have them all models. So we have a good sampling and co-located sampling of all these properties. So again, you can look at like where the high densities are, or low resistivities, or high susceptibility values. So the next level you can do, usually as a data analytics, you can look how I can cluster these things. You can choose like something like K-means or some more sophisticated clustering methods. Again, I tried many of these things, and you can see that when you cluster them, it just goes arbitrarily, picks something, somehow based on the center of gravity or different criteria, you can cluster these. And then once you cluster them, and you can just put them back to their locations and see, they could be like, you can interpret that these are the same property and see how much they match to the surface. I had a hard time to really match anything meaningfully to what's going on the surface, lithology. I did that. Now this is another kind of clustering. And again, doing this, some of them matching to some extent, but again, the other clusters didn't have. So I gave up on this, and I changed my approach. I said, what I'm gonna do, I have this 3D cube of my values. I'm just gonna go find the medium value of the resistivity, susceptibility, and density, and I'm just gonna divide it in 8 groups. Like in this cube, I have 3 parameters, low, high, low, high, low, high, and I can divide them in 8 different categories. So if you do that, so you can have a low resistivity, low density, and here low susceptibility will sit in here, high susceptibility of this will sit in here. So you pretty much now, we divide in like the simple idea of where's the high and lows of these parameters are and when they are located. So once you have that, and you can go, okay, well, I have that one, let's go on our lithology and then divide those in different groups. And that's what I did in here. Take lithology, I call them FV, MV, FI, MI. So it's just sedimentary mafic. So it's just the simplest way of like dividing these in different groups. Now I have the surface. I know what is in the surface. I know at different depths what I have the low and high resistivity, that those 8 groups. Now I can see if there's any correlation between these concepts and try to find if there's a meaningful correlation between these values. So on the top you see my felsic volcanic, mafic volcanic, felsic intrusion, mafic intrusion, and sedimentary. And like here I'm putting high density, high resistivity, high susceptibility at depths of 250. So I'm going to repeat these for all these depths. So what you do, we call them cross correlation. If one of these things really matching the other one, here meaningfully you see mafic volcanics, they look like close to the high densities. What would happen at the 0 and 0, you will get a high peak. That's the correlation value. Right happening at the center. If there was a shift, this thing MV matching this, but if it was shifted horizontal location, that peak would happen a little bit shifted and then somewhere to left or right or anywhere. So you do these for all these depths. You do it like now I'm going a deeper level and I'm assuming whatever's on the surface somehow relates what's happening in the deeper and deeper parts. And I do all these correlations. It's going to end up lots of simulations, there's lots of values, so I have to summarize this somehow. And again, I'm going at a deeper level. These are still high. I can do this for the low density, low resistivity, low susceptibility parts with all these things on top and find their correlations. It's hard to see what's happening here, so I'm just going to codify these for you. So again, let's go to our whole Metal Earth projects. These are all our data, so I have 11 zones that I have all these analysis and regularized and all these data. So to be able to what I did in the cross correlations, to show them in a simple way, I put Abitibi 6 transects in here, starting from Shibugamu all the way going to Swayze. And as you go down, they will represent different depth from surface to the 7 kilometers. And the little gap, and then I will show these things, whatever you see, these 5 columns, they show what's happening in Wabigoon. So now I'm gonna go show that high res and the correlation that's happening with different ones in one location. So this plots in here shows high density, and again, remember these 6 lines are the Abitibi, and the 5 and this little rainy river is, we don't have a whole depth, so a smaller one. The one that I could see in here that clearly popped up, it's mafic volcanics and high densities. They're really matching. We have a really good, right at the 0 locations, at that location, at all depth, that density, and also low density with felsic intrusions. They're very obvious. The rest, I had hard time to really make sense of it. Then going in here, this shows the correlation value. Again, going up and down in here, this shows where the correlation happening, almost at 0, right at their locations. And this shows how much that correlation was, the value of like 60, 70%. And those are the most significant ones. There's some little low susceptibility stuff, but I really had a hard time. So the problem was like how much these are reliable, and the fact that our gravity, density, and susceptibility, they're nicely sampled. I wasn't worried about those. What I worried about the resistivity, because they're pretty much along the transects, and I feel like after 5 kilometer buffer, we're losing our resolutions. So all these data that I had already, so most likely Ahmed Reza, they're going to talk about, we gave these to our data analytics people, and they confined them around those 5 kilometer gaps, and Ahmed Reza is going to talk about those analyses, and they applied on these data to see what is the exact data analytics interpretations we can get out of these. And these are like some simple, you can look how much shifted to northeast, you can know how that cross correlation gives us. But again, I was more not like for the resistivity ones, I wasn't sure what we're getting. Just that takes me to the conclusions. Again, we find like even though we had our seismics, they were good. having one independent, and again, that passive seismic gives you something that the same nature of our reflections. They're all velocities. When you're talking about the resistivity, it's totally a different property. But like passive seismic giving you the shear wave velocity that you can really one-to-one match with your seismic reflections. And that gives you very interesting results that you can interpret like whatever you're seeing there on the lack of any kind of drilling abilities that we can have at these crustal scales. And again, going to those density and susceptibility and resistivity things, what I found interesting is that clustering as like throwing these there, it doesn't really give something. So we tried to go some median value segmentation and making sure that we can look at these in a more systematic high and low and get something maybe meaningful out of them. With that, I thanks all our colleagues and everybody that really helped us with these. And these are some references that I mentioned if you want to go later look at it. Thank you.